Okay, good morning everyone. Today we're looking at the next couple sections in chapter 6, which is 6.2 and 6.3. Your textbook separates them, but there really is no need to do so. So we're getting to the point where we want to use vectors to solve real life problems. Today we're not going to be there, but our next lesson we will. So we're going to start building today. So to add or subtract, we add or subtract vectors to determine a resultant. So I just threw out a couple examples here. So one example is when a plane steers in a certain direction, a wind comes from a different direction, right? The wind's going to cause the plane to move. So if the plane wants to go to a particular location, it's not necessarily going to steer to that location. It's going to steer to compensate for the wind, okay? So I just said here that the plane's final speed and direction is the resultant vector. Okay, so today we will apply operations to vectors. And next lesson we'll add the context. So to add vectors geometrically, we simply place, let me fix that there. No, we place the vectors tip to tail. Okay, place the vectors tip to tail. Oh, here we go. Let's see here. Okay, let's get rid of that now. No. Okay, so for example, oftentimes in a diagram you're given vectors that look like this. Maybe like that'll be like vector A, and that'll be vector B. So right now they are tail to tail. Okay, that's not how we add them. So what we do here is we actually just take the vector, like one of them, doesn't matter which one, and we slide it so that they are tip to tail. So we can slide vector A, and then we start here and we go to here, and this is called our resultant vector A plus B. Okay, similarly, you could have slid B up to A and you would get the exact same vector. Okay, it doesn't matter. So to subtract vectors, okay, we simply add the opposite vector. Okay, so for example, suppose we have like, that would be like vector A, and then this right here would be vector B. Then A minus B, we would simply just switch the direction of B and make it point this way. And then our resultant would be right here, which would be A minus B. Okay, we'll see that in the example to follow. And then to multiply vectors by scalar, we simply multiply the magnitude. Okay, and the direction does not change. Okay, and it's also important to know that a lot of our properties, algebraic properties, apply to vectors as well. So for example, our distributive property, so remember a scalar is just a letter without the arrow. Okay, so let's say A times vector U plus vector V. Okay, that is equal to A times U plus B, or sorry, A times U plus A times V. Okay, and similarly when we're adding like terms, right, we just add, like, so if I want to simplify, like 2U plus 3V plus 5U minus V. Okay, it follows the same rules as like terms. You just add like vectors. We have, that would be 7U plus 2V. Okay, you'll be asked to verify a couple of these properties in the assigned work. Okay, so here's the example. So given vectors A and B, determine the following: A plus B. Okay, so I like to draw out vector A first. So we have vector A is going this way here. and vector B is going this way. So again, I start the tip, right, like that, and then there is our A plus B. Okay, A minus B. Okay, again, I showed you above there, we have A, and then minus B means we're going to draw it the opposite way. And here is A minus B. Okay, and now 2A plus B, what we're going to do here now is we're going to draw A so it's twice as long. So we'll just say it like that, and then plus B. And there's our vector 2A plus B. So next unit we'll actually have like, or next section rather, we'll actually have like A and B as magnitudes with directions, right? And then we'll be using trigonometry to find the resultant, right? Or Pythagorean theorem if it works. Okay, so this one right here is just a definition. It says if U and V are vectors and A or B are scalars, scalars just mean numbers, then A times U plus B times V is called a linear combination of U and V. Okay, and that's what it is there. Okay, and now for the example. Okay, simplify the following. Okay, these are ones that we sort of just looked at, but I'll give you another one here. Let's suppose that we have, let's say, 4 times U plus V minus, let's say, 2 U minus V. Okay, so what we do is we use our distributive property. So we have 4U plus 4V minus 2U plus 2V, and that is equal to 2U plus 6V. Done. All right. Now, last example here. So consider the parallelogram, ABCD, and then we have the E is the intersection point of the two diagonals. Suppose vector U is equal to AB. So this is vector U. And V is equal to BC. That's vector V. Express each in terms of U and V. So first one is AC. Okay, so AC is equal to AB plus BC, or just U plus V. Okay, you should have a line over top there, so this is equal to U plus V. All right, next one, BD. So if we go BD, so we always start at, because B is written first, start at B, so BD is equal to, okay, there's different ways you can look at it. You can do it from BC to CD, right? So I'll write it like that first. So this would be like BC plus CD. Okay, but I said write it in terms of U and V. So we know that BC is V, and then CD, from C to D, is actually negative U. So that is negative U, right? Because it's going in the opposite direction. So this is equal to vector V minus vector U. Okay, and next one, AE. So we're going from A to E. So again, there's two ways you can go. We can go this way here first. So we can go A to like some point here, and then we can go up like this. Okay, and what we have here is that this is actually half of V, right? There's the other half, and this is half of U. So it's just going to be half U plus half V, or 1/2 U plus V. I don't care which way you write it, it's the same thing, right? This is sort of factored form. Okay, excellent. And there is your work for today.